All right, we're going to look at acid-base titrations. And what happens when we do this is we combine a solution of known concentration and volume with another solution whose volume we know but whose concentration we don't. And we can take a look at the variation of the pH with the amount of titrant that we add, and we can get a very interesting looking curve which tells us a lot about the solution. All right, so looking at part A, the point at which stoichiometrically equivalent quantities of acid and base have been brought together is called the equivalence point. And this point can be noticed if you add an indicator solution such as phenolphthalein. The solution changes color at this point. It's quite dramatic and quite sudden, so it's very easy to determine this equivalence point. Or you can use a pH meter. This produces a pH titration curve, and this is in fact what you will be doing on the exam. All right, so the solution in the burette is what is the known concentration, and that's called the titrant. And we add this into the burette, or add this into the flask or the beaker of the other liquid, which is called the analyte. And if we were to graph our volume of titrant added versus the pH of the solution for a strong acid and a strong base, for example, sodium hydroxide with hydrochloric acid, we would get a curve that looked like this. This is for the addition of the base to a flask containing acid. Starts out at a low pH, rises dramatically in the middle, and then levels out. All right, let's do some calculations. And for this, you must get your calculator and follow along with the calculations. You're going to need to stop the video so that you can write some things down. Otherwise, I'll move too fast for you to keep track of what's going on. So we've got an experiment where I've got a burette containing 0.1 molar sodium hydroxide, and the flask itself is 50 milliliters of 0.1 molar HCl. So you can see I have a strong base. I'm added to a strong acid. They both have the same molarities. This is about as easy as the problem can be. And the initial pH of 0.1 molar hydrochloric acid, because it's a strong acid, is going to be 1.00. Now, after we've added 49 milliliters of this 0.1 molar sodium hydroxide, we have the following stoichiometry. Our initial moles of HCl, which is simply the volume times the molarity, will be 0.005. And at this point, after 49 milliliters, I have excess hydrochloric acid of 0.0001 moles. Now, how much sodium hydroxide have I added? I've added 49 milliliters, which would be 0.0049 moles. And the total volume of solution is now the 50 milliliters of acid plus the 49 milliliters of base, or 0.099 liters. And this is going to give me a concentration of 0.0001 moles divided by 0.099 liters, or approximately 0.001 molar, which gives me a pH of 3. Make sure at this point that you can do these calculations and you understand, rather than just nodding your head going, yeah, because you will have to do this. All right, next part, part E. I've gone from 49 milliliters to 50 milliliters. Now, I'm at the equivalence point because the number of moles of sodium hydroxide I've added are equal to the number of moles of acid that I had initially. And at this equivalence point, the pH is equal to 7. It must be 7 for a strong acid, strong base titration, because both the cation and the anion that are formed are neutral and they don't affect the pH. All right? Now, I go from 49 to 50. Now I'm at 51 milliliters. I've added slightly more sodium hydroxide than I needed to neutralize the acid. So now I've got this. initially, 0.005 moles, but now I'm 0.0001 moles in excess of hydroxide. So the total number of moles of sodium hydroxide I've added is 0.0051. The total volume of solution is 50 plus 51, or 0.101 liters. So my OH minus concentration is 0.0001 divided by 0.099. It gives me 0.001 molar. And that gives me a pOH of 3, but a pH of 11. All right, now, this is interesting because in the space of just 2 milliliters of added titrant, so in other words, from 49 to 51 milliliters, the pH has gone up from 3 to 11. This is a 100 million fold decrease in the amount of H plus, molar concentration of H plus. Truly dramatic pH change. If I were to graph a curve like this, it would look like this. The one on the left is where I've added the sodium hydroxide to HCl, and the one on the right starts with the sodium hydroxide and adds HCl to it. It's just the other way around. And you can see that these curves are mirror images of each other. All right, now, step H. Let's kind of back up and look, what does this tell us when we do a strong acid, strong base titration? Well, the initial pH is very low, and as I add the titrant or the strong base, the pH increases slowly at first, and then in the vicinity of the equivalence point, it just rises dramatically, just very, very quickly with little volume change. At the equivalence point, the pH is 7, because the salts that are in there are neutral. They don't affect the pH. And after the equivalence point, the pH of the solution is very high. All right, that's the strong acid, strong base titration. Now let's take a look at the weak acid, strong base. And of course, you may ask yourself, well, is this really going to be any different than a weak base, strong acid? The answer is no, not really. The curves will be mirror images of each other, but they're they're different than the strong acid, strong base. Right now, what I've got is 0.1 molar sodium hydroxide that I'm adding to 50 milliliters of 0.1 molar acetic acid, and they give us the Ka. So acetic acid is a weak acid, so the pH of this should be greater than 1. Well, let's see what it really is. When we do this equilibrium pH calculation for a weak acid, which I'm hoping by this point is somewhat second nature for you, we set it up this way. We solve for X, and we get 0.0013 molar, and the pH is 2.89. We said the pH would be higher than 1, and in fact, it is higher than 1. All right, the next one. After I get halfway to the equivalence point, 25 milliliters have been added to the flask, and I've got the following stoichiometry. But let's take a look at what reaction I'm doing. I'm adding hydroxide to a weak acid. So despite the fact that it's a weak acid, it's a strong base. And so this strong base is forcing a one-way reaction to produce this acetate ion and water. All right, our initial moles of acetic acid, 0.005, and 0.0025 moles of base have been added. That's just taking the concentration times the volume. The moles of acetic acid present in the solution, well, I've consumed half of them. So I've gone from 0.005 to 0.0025, and I've produced that many moles of acetate ion because stoichiometry says that I have. All right, now, if I use Henderson-Hasselbalch to calculate the pH, I'm going to get something that looks familiar. At the halfway point, a buffer solution exists in which the moles of weak acid are equal to the moles of the conjugate base, and at this halfway point, the pH is equal to the pKa. And this is what the curve looks like. You can see in red, this is the outline of the original strong acid, strong base we did, but the blue is going to be what the weak acid, strong base looks like. And at the once the equivalence point has been reached, the curves are identical to each other, so not terribly interesting. What's interesting is what happens beforehand. All right, now, question M, or problem M. After 50 mils of this 0.1 molar sodium hydroxide have been added, I now have 0.005 moles initially, but I've added 0.005 moles of sodium hydroxide. So now I have 0 amount of acetic acid left in the burette, and I have 0.005 moles of the acetate ion, and the total volume of the solution is 50 plus 50, or 100 milliliters, 0.1 liters. And the acetate ion is now 0.05. All right, in the strong acid, strong base titration, the pH at the equivalence point was 7 because the salt that I manufactured, sodium chloride, doesn't do anything to the pH. But when I have a weak acid, strong base, the salt that I make doesn't behave the same way. So here I have sodium acetate, and sodium acetate behaves as a base in solution. And let's look at why. We want to write the net ionic equation. So I'm going to write acetate ion plus water reacts to form acetic acid plus OH minus. Now the Ka for acetic acid we know is 1.8 times 10 to the minus fifth. I can compute the value of Kb for acetate ion because I know it's just Kw for water divided by Ka for the acid. And I get 5.6 times 10 to the minus 10th. Part P, the concentration of acetate in solution at the equivalence point of this weak acid strong base titration is equal to 0.050 molar. Use the Kb expression to calculate the pH. Well, I can write the Kb formulation, and I get this, and I set up my equilibrium expression, and I'm going to assume that X is negligible relative to 0.050. And when I do, I solve for X, which is the OH minus concentration, and I get 5.3 times 10 to the minus 6. When I take the negative logarithm of that number to get POH, I see that that's 5.28, which means my pH is 8.72. Now, part Q says after 51 milliliters of this has been added to the flask, and now I have this stoichiometry. I'm a little bit past the equivalence point. So I've got this amount of material added. So my OH minus is 0.00099. My pH becomes 11. Now, let's take a look at the differences for these titrations. A solution of weak acid has an initial pH that's higher, all right, because the acid isn't as strong. Therefore, I have less H plus manufactured. And at the halfway point in this titration, the pH is going to be equal to the pKa of the weak acid. Near the equivalence point, which is the rapid rise portion of the curve, it's smaller. The rise portion is just shorter because I'm starting at a higher pH. So the pH at the equivalence point is going to be greater than 7 because the salt behaves as a base. It shifts the pH higher up. And after this equivalence point, though, as I mentioned earlier, the titration curves are going to appear very similar to each other. All right, we're going to stop here, and we'll pick up with a polyprotic titration in just a minute.